This is SPYthon, our project for Polito programming for IoT exam. It consists of an IoT terrarium, a smart device which grants monitoring and remote control for every reptile owner.
The catalog is the reference for all the actors in the system to get information about the registered devices and users. It is written as a JSON file, and at startup, the only available information is the address of the MQTT broker. The devices that have to register are Terraria, that are the Raspberry Pis, temperature controls, and light controls. These devices are automatically deleted from the catalog after 30 minutes of inactivity. The catalog is responsible for communicating to the controls the changes in their configurations. Lastly, users are registered in the catalog via Telegram.
The lowest level of our application is represented by the device connector. It is divided into two main subsystems, the one dealing with sensors and actuators and the other dealing with the web implementation. In the first one, the Raspberry Pi has been physically connected to the sensors and to the actuators. The used sensors are temperature sensor, reading the temperature values in the terrarium, humidity sensor, collecting humidity values. Those are both wired on the same sensor, the DHT22. Light sensor, communicating the status of the light, if on or off. It has been simply emulated by a wire, since the stages are only two. Lock sensor, communicating where the terrarium is open or closed. This has been emulated by a single wire too. Camera, sending images of the reptile when needed. It has been emulated with stock photos on the Raspberry Pi memory. The activated actuators are an heating cable, represented by the heating system, controlled by a relay, and the proper reptile light, represented by a lighting system, controlled via smart plug. The second subsystem is the web implementation of device connector. All the data collected by physical device connector are communicated to the other actors of SPYthon by the internet. The web device connector is responsible for establishing communication with the connected devices through two main internet protocols, RESTful services and MQTT. RESTful services are implemented by Cherry Pi, performing simple GET method, are useful for user awareness. They can send temperature, humidity, log status, light status, and a photo when requested. Publisher-subscriber communication is performed by PowMQTT using an external broker. The web device connector has to publish periodically, with threads, on proper topics all information useful for the control strategies and for data processing such as temperature, humidity, log status, and light status. The device connector is also a subscriber for topic used for actuating the heating system and the lighting system and other information that can be requested by the user.
Control strategies are meant to be habilitated by the user through the Telegram chat and set as desired through REST services. Light control and temperature control are separated web services, both composed of a web interface and a control core. The temperature control is activated through REST services by the user setting a reference temperature and perform a comparison between the current temperature and the one set by the user. If the temperature is below or above the acceptable values, the corresponding command is published through MQTT. The temperature margin are expanded according to a reasonable tolerance of ±1 degree, and the target temperature is adjusted depending on the illumination condition. If the animal is experiencing nighttime, the temperature is lowered by 4 degrees, respecting the animal's need. The illumination conditions are retrieved through MQTT. A control on the humidity is also performed, receiving the humidity through MQTT and compare with a value stored in the configuration file. Again, a tolerance is introduced of about 6%, and if the humidity value is out of scale, an alert message is published through MQTT. The reason why we do not try an active control is because in most cases the humidity is regulated by means of a water bowl, not an IoT device. The light control is again activated through REST methods and perform a comparison between the current time and the rest and stop time. These are defined by the user and are exploited to publish an activation-deactivation message through MQTT. At activation time and deactivation time, no action are performed to allow the user to smoothly introduce the IoT control over the manual switching.
The Telegram bot is an interface to the user. Firstly, a new user is invited to register. The user is stored with a nickname and with the chat identificator, used to send notifications. Then, the user must be associated to an already online terrarium, giving the terrarium name and the password. Only the user associated with the terrarium has access to it. We can check how a reptile is doing, getting temperature and humidity information, checking that the terrarium is closed, and asking for a photo of our pet. We also receive notifications if the humidity is over the acceptable limit for the health of the animal. Through Telegram, we can also set the reference, the time temperature, and the hours of dawn and dusk inside the terrarium.
In order to give more feedback to the final user, a data visualization service is implemented using ThinkSpeak and Freeboard. Data sent by the broker via MQTT are collected by the ThinkSpeak adapter and then published via HTTP on channels provided by ThinkSpeak. ThinkSpeak allows an easy representation through graphs and widgets. We created 4 channels, one for temperature, one for humidity, one for light status, and one for power consumption. Freeboard provides a dashboard for a more user-friendly visualization. It will be sufficient for the user to open Freeboard to have a complete report of his IoT terrarium. On the dashboard there are a photo of the terrarium, actual temperature, humidity and light status widgets, graphs of single-day temperature and humidity live updated, power consumption counter relative to the actual month.
you.